All right, we are given this complex number in this form, and we need to convert it to the form a plus bi. So when we consider complex numbers going from real numbers, we can kind of visualize it like so. So when we think about a regular number line where it's like 1, 2, 3, 4, 5, so on and so forth, they're all real numbers. They're all a part of the real number element set. But we also have the imaginary set. So that's when you get, so I by definition is square root -1. Obviously you can't compute that, but that produces the complex number I, and the complex number I is pretty much a quote-unquote y-axis for the number line. So we have like a left and right, which is like going positive and negative values on the number line, and then we also have up and down, which is the positive and negative complex numbers. And then from that, we get the form a plus bi. So a is the real component of this complex number, and b, the coefficient of b here, is the complex pretty much coefficient. And so we can see here, if we look at a, I don't know, let's do 1 plus 2i. If we look at the real axis, that's just 1. And then if we go up to the imaginary axis, that's 2. And then from here, we generally think about the number line as just a straight line, so you can't like go up or down. And when you find the absolute value, even if the number computed is negative, the absolute value of it will be positive because it's the distance from a reference point, in this case 0. But if we take that logic and apply it to complex numbers, we can realize that the absolute value of a complex number is the distance in 2D space away from the origin point, in which case this is 0. And this should look familiar to you, because from that we formed a right angle triangle, and we can just use Pythagoras to find the absolute value. But in this question, we don't actually have to deal with absolute values. That was just an explanation of how to find it using complex numbers. But pretty much, let's go straight into the question. So what I would do first is, well, there's a surd here. We can take the complex conjugate of this, and so if we split that up, we get z is 1 plus I over I minus square root 3, and then multiplying the complex conjugate will give you I plus square root 3 over I plus square root 3. Because remember, when you take the conjugate of something, of anything, it changes the minus to a plus or the plus to a minus. And then from here, we can just do some simple expanding. So if we look at the definition of I, it's square root of -1, right? So we can see here that we get I times I, so I squared. And obviously, if you square square rooted number, you just get what's inside the square root. So I squared equals -1. And that's a good thing to memorize. You do not want to get confused when expanding brackets like that. So, and then we could just represent 1 as 1 over 1. So it doesn't really affect anything, so we don't really have to take that into consideration. But if we expand this top, we get -1 plus I square root 3, because remember, you're just multiplying out the I and the square root of 3. It doesn't actually change anything, because it would still be square root -1 square root 3. And then on the bottom, we get, again, be careful, I squared -1 plus I square root 3 minus I square root 3 minus 3. Because remember, square root of 3 times square root of 3 is just 3, and then you got the minus there. And you could honestly, you could have realized that that's just the squares definition, so you didn't actually have to do this central term, because that just cancels out to -4. So if we go back, or we should probably do the 1 plus there. So if we go back and simplify all this stuff, we get z equals 1 plus -1 plus I square root 3 over -4. Because those terms, it's 1 minus 1, for example, it's just 0, so that cancels out. And if we further simplify this, we get z equals 1. So what I'm going to do is I'm just going to break it into sections. So we get -1 over -4 plus I square root 3 over -4. It's still the same thing, because if we just add the fractions together, we get the same result. But from here, we can simplify that further to 5 over 4 plus I square root 3 over -4. And this would be the answer, besides the fact that we have to explicitly state or explicitly give the values of the real constants a and b. So in this case, a, so if we go back to the complex number, it's a plus bi. And so a is 5/4, and b is, well, it's just multiplying I by square root 3, and then it's all over -4, so it's just negative square root 3 over 4, and that's your answer. So again, when we think about complex numbers, we got an x and y axis. The a is the real part, so 5/4 would be like, I don't know, there. This is not going to be to scale. And then the complex is the complex, the complex component of the complex number itself is in the y-axis. So just remember that. And then remember, when you're squaring or multiplying I times I, it's -1. I squared, same thing. And the definition of I is square root -1. And this ties into discriminants and quadratics. So I'll kind of give a short overview of this. So when we get the discriminant of a function, remember the quadratic equation is -b plus minus the square root of b squared minus 4ac over 2a. And whenever you get a calculator error, basically that means that this b squared minus 4ac is a negative number, because again, anything like a -4 does not compute. It's a complex number. -1 is the definition of a complex number. So that's why you get a math error there. And that's why when you learn discriminants, if you do delta, which is the discriminant, is greater than 0, then you get 2 roots. So if we do this, we get like 2 points of intersection here and here. And then if we get delta equals 0, we only get 1 root. So it will kind of like touch the axis and then bounce back out. But if we get delta is less than 0, that means it's a negative number, which means that there's no points of intersection, at least in the Cartesian real space, because, well, if we look here, it doesn't actually cross the x-axis at all. And it does get kind of complex when you try and graph this stuff where you don't have a real solution, but rather you have a complex solution, and it kind of does some weird transformations to the graph in 3D space. So again, this would be like a real space, and then imaginary space would add a third axis or another axis, just like if we were thinking on number lines, we have the x-axis as the real and the y-axis as the imaginary. So yep, that's pretty much it for the basics of complex numbers. See you later.